Hi, Mr. Gibson here. This lesson is the first in our lessons on the unit of sequences and series. And in this lesson, we're going to take a look at mathematical patterns, really an introduction to sequences and series. So let's look at our objectives here. We have two objectives. The first is that you will get some practice identifying mathematical patterns and be able to describe how we get from one number to the next in the pattern of numbers. The second objective is to then be able to use a formula, or actually two different types of formula, for finding the nth term of a sequence. Now, this is a term we're going to talk about a little more, but what do we mean by the nth term of a sequence? It just basically means we could find any term in the list of numbers, whether it's the first term, the 10th term, the 100th term. So the formulas will help us to be able to do that. So let's think for a minute about the superstair problem that we just reviewed in class and that you worked on. Here you created really three different number patterns. The first is just simply the number of stairs. Now I just listed up to 8 here, right? But we had a total of 21 stairs in this problem. The second is the number of steps or super steps. So this is the number of steps to go up and down for a given number of stairs. And that created this pattern of 2, 4, 6, 8, 10, etc. And then the third pattern we created was the total number of steps. So this is simply adding kind of the cumulative total of the number of super steps. So that gave us the 2, 6, 12, 20, all the way up to over 400, right? Our total was over 400 for 21 stairs. So here's the question. These different patterns that we generated, are these a sequence or a series? Well, before we try and answer that question, let's define what these terms mean, and then we'll come back and see how they apply to our superstair problem. So first, let's start with a sequence. It's simply an ordered list of numbers, okay? That's all it is, just a list of numbers, but they have a specific or unique order to them. It does matter what order we put them in. Each number in a sequence is a term. Okay, so it can have anywhere from one to many terms in the sequence or list of numbers. Now, a series is the expression for the sum of the terms of a sequence. So whatever numbers we have in our sequence, in that number list, we add them up and get the total. That's what we mean by a series, right? So this is the key part right here. That's the sum of all the numbers in our list or sequence. Now, we can have two types of either sequences or series. The first is that it's finite. And when we say finite, it means it has a limited number of terms. And we can count those from the first term 1 to the final term, which we're going to call n, would be the total number of terms. Okay? The key is that it's finite. We have a certain number that we can count to. The other, as you might guess, would be infinite. And an infinite series or sequence continues without end, okay? So it has an infinite number of numbers in the list. So let's look at a couple examples of those. Here's a finite sequence, right? It's simply a list of numbers, 6, 9, 12, 15, 18. In this sequence, right, we have a total of 5 terms, right? 5 different numbers in our list. Here's what a finite series might look like. And now you can see where we're taking the sum, right? We're simply adding these same numbers in the sequence, but now it becomes a series. So these are finite. They each have 5 terms in them. One is just a list. The finite series is the sum of those numbers. Now, an infinite sequence, we would list the first few terms, 3 or 4 or 5 of them. And then to show that it goes on forever, we put these 3 dots here, dot, 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 okay? That just means that it keeps on going forever. Same thing with an infinite series. We would show the addition of the first 3 or 4 terms, and then we put the dot, dot, dot there. And it tells us that we're just going to continue to keep adding each of the next terms forever, really, right, to infinity. Okay, so here's our definition. Make sure you get these in your notes. These are important terms we're going to use throughout this unit. So if you need to pause the lesson, go ahead and do that and finish your notes here. But now let's go back to the question we had in our superstair problem. Did we create sequences or series? Well, the answer is both, right? The number of steps, this was a sequence, right? It gave us a number pattern, 2, 4, 6, 8, 10, 12. Now I put dot, dot, dot because I'm not going to list them all out, but the last 3 terms on your list were right 38, 40, and 42, right? 21 steps or stairs would take 42 steps. So we created a sequence, a finite sequence. The total number of steps is a series, because how did we get those numbers? We got it by adding up the sequence. So we took our sequence, turned it into a series by simply adding them all up. And that's how we got our total of over 400 steps. So both of these are finite. N represents the total number of terms. So in this case, we had a total of 21 terms, 21 stairs. Okay, so here's the basic difference, right, between a sequence and a series. One is a list of numbers, the other is the sum of those numbers. All right, so let's look at some examples. I'm going to give you a pattern, and I want you to describe the rule that tells us how we get from one number to the next in that pattern or list. And then tell me what the next 3 terms would be. So let's start with our first, okay? This would be an infinite sequence, right? It shows the first 4 terms, but dot, dot, dot means it goes on forever. But here's the question, right? How do we get from 27 to 34, from 34 to 41? Really what we're doing, right, is looking at the difference here. How do we get from one term to the next? Okay, so if you look at this for a minute, you start to see that the difference, right, between these terms is 7. So here's our rule, right? We would add 7 to get from one term to the next. So if we wanted to produce the next 3 terms, we take 48, right? Add 7 more and we get 55, right? All we're doing is adding 7 each time. Same thing, 55 to 62, and then 62 to 69. Okay, so let's look at another one here. 243, 81, 27, 9, and then again, it's an infinite series, or rather sequence. So how do we get from 243 to 81? Well, it's smaller. So you could first say, well, am I subtracting the same amount each time? But if you start to look at these differences, right, it's not the same difference each time. So what's the other way we could make it smaller? Well, we could divide, right? So let's look at these numbers. If the big numbers aren't obvious or we don't have a calculator handy, let's do it between the smaller numbers, right? So 27, how do we get to 9? Well, we would divide by 3, right? And 81 divided by 3 would also give us 27. So we'd have the same operation there. And if you grab a calculator, 243 divided by 3 would give us 81 as well. Okay, so in this case, the rule would be divide by 3. The next 3 terms, right? We take 9 divided by 3 would give us 3. 3 divided by 3 is 1. 1 divided by 3 now gives us a fraction. So here's our rule. Simply divide by 3. Okay, so in the assignment today, we're just going to begin to get some practice at looking at sequences of numbers and seeing if we can determine the pattern, the rule, and then generate the next few terms. Now, the next step is to look at formulas that we can use to generate mathematical patterns. Now, when we use a variable in this formula, we're going to really use two key variables. The first is the letter A. And letter A, with a positive integer subscript, represents the terms in a sequence. Okay, now let me show some examples, and this will start to make some sense, right? Let's say our first term is represented by the variable A, and because it's the first term, we're going to put this little subscript 1. Subscript just means a smaller number that's written a little bit below the variable, okay? But that 1 means it's the first term, right? So the second term we could write as A, again, the value, and then the subscript of 2, saying it's the value of the second term. And then so on. The third term would be A sub 3. Okay, so this is how we're going to represent the notation that we're going to use to write these terms. Now let's make this more general. Let's say we want to write expression for the nth term, but 1 just before that, right? So again, the nth term is some term out in the sequence. It could be the 10th, the 100th, the 1000th, okay? Whatever that last term is in the sequence. So if we want 1 just before it, we would write that as n minus 1. The term itself that represents n, we would just use n. If we wanted to put one more term after n, right, then we would just add 1 to it. And so the subscript would be n plus 1. Okay, so this is kind of the general form of the notation that we'll use for any term in the sequence. Now, let's talk about the first type of formula that we're going to work with. A recursive formula defines the terms in a sequence by relating each term to the one before it. Okay, so basically, if we know the first term, then we can find the second one using a recursive formula, right? But we can't find the second term unless we know the first term already. Okay, so this is not as useful as the other formula we'll look at, but it is usually simpler, right? We can simply figure out what do we need to do to get to the next term using the term before it. So that's what a recursive term does, right? It just allows us to find the next term based on the previous term. So let's look at an example where I'm going to give you a pattern. I want you to figure out what the rule is and then write a recursive formula for that pattern or rule. So here we go, 2, 4, 6, 8, 10. Now, that's a pretty simple pattern. I think everyone can see we're simply adding 2 to get to the next term, right? If we want to get from 2 to 4, we're just going to add 2 each time, okay? Now, how do we take that operation, add 2 each time, and write it as a recursive formula? Well, here's what it looks like. The recursive formula always starts with a sub n, right? So this says if we want to find the nth term, and at this point, n doesn't have a value. It could be the 5th term or the 10th term or the 20th term, right? N is just a variable for which term we're finding. But we start out with an equals, and then since a recursive formula gives us the value if we know the one before it, we're going to write the term before it as a sub n minus 1. Okay, so that means 1 before an, just like we saw in the previous slide. And then, what's the rule? Well, in this case, we're adding 2, so we just put plus 2. Now it's as simple as that, right? To find the nth term, we take the one before it, n minus 1, and add 2. Now there's one more detail we always want to include in our recursive formula, and that is, what's the starting condition? In other words, what's the first term? Because if we know the first term, then we can find the second. And then once we know the second, we can find the third. So in this case, we just go back up to our original problem, right? Up here, the first term is 2, so we're just going to take that and put it down here and say that the first term, a1, is equal to 2, okay? But that's an important kind of little detail that needs to be included when you write the recursive formula. So there's a simple example of how we would come up with the recursive formula. Now, let's use it. Let's say we wanted to find the 6th term, okay? Now, if we go back up to the original problem, we see we had 5 terms, 2, 4, 6, 8, 10. So to find the 6th term, we start with the 5th term, right? 1 before it, and add 2. Well, let's just put in what that 5th term is, 10. And then we add 2 and we get 12. So the next term in this sequence would be 12. All right, let's try another one here. I'm going to pause for just a few seconds so you can pause it and see if you can figure out what the pattern is here. 6, 1, -4, -9. Okay, so hopefully at this point you can recognize that the pattern is that we're subtracting 5 each time to get to the next term, right? So 6 minus 1, or 6 minus 5 is 1. 1 minus 5 is -4, and so on. All right, what would the recursive formula look like? So again, we start with a sub n equals, and then we're going to take the term before it, a n minus 1, and in this case, the operation is subtract 5. Okay, so as simple as that. Don't forget to put the starting condition. So a1 would be equal to 6. Now let's use this to find the next term, the fifth term. Okay, so we're going to take the fourth term and then subtract 5. So the fourth term is simply -9. So -9 minus 5 gives us -14. So the next term in the sequence would be -14. Let's say we wanted to find the sixth term. Well, we'll take the fifth term we just found, which is -14, subtract 5, and we get -19, and so on. Okay, but you'll see that the recursive formula really just lets us find one term at a time as long as we know the previous term. All right, the other kind of formula, it's a little more complex, but quite a bit more useful, is called the explicit formula. And it expresses the nth term in terms of n. In other words, n is part of the formula. And it allows us to find any term in the sequence. It could be the 5th term, the 10th term, the 100th term, without having to know any of the other terms. Okay, so this one's a lot more useful. So let's take an example and see if we can come up with these explicit formulas. This table shows values for the sides of a square. And we want to find the length of the side, the perimeter, and the area of the square. Okay, so we're going to have a whole series of squares that are going to keep getting larger and larger and larger, right? They all have 4 sides, but the first term is going to have a length of 1. Right? That's what this is telling us right here. And you can see down here in the example, right? Here's our side that has a length of 1, right? Both sides do. Okay, so for n equals 1, the first term, the length is 1. What would the perimeter be? Well, how do we find the perimeter of a square? We just simply add up the 4 sides. So 1 plus 1 plus 1 plus 1 gives us 4. Okay, that's where the perimeter comes from. The area, if you remember, the formula for the area is the length times the width. Okay, so since both length and width are 1, 1 times 1 just gives us 1. Okay, so that's what the table looks like here. We're going to be generating the list of numbers for really 3 different sequences here: length of the side, perimeter, and area. Okay, so the second term, now you notice the length goes to 2. So we still have 2 here, but 2 times 4 for the perimeter gives us 8. 2 times 2 gives us the area of 4, and so on. Okay, 3 times 4 is 12, 3 squared is 9. And we could fill in the rest of the table here. Okay, would look now let's write the explicit formula for the length. And the way we do this is, you can see I put these arrows up here already. We're going to look at what is the value of n, and then what is the value in the sequence. So for n equals 1, the length is equal to 1. For n equals 3, the length is equal to 3. For n equals 5, the length is equal to 5. So in this case, it's pretty simple. Whatever the term number is, that is also the value of the length. Okay, so the equation is very simple. Just a sub n equals n. Whichever term it is, that's how long the length is. Now let's look at the perimeter here. Okay, so here we're going to compare the term number n to the perimeter. So we go from 1 to 4. 3 to 12, 5 to 20, right? So what operation are we doing to get from the n value to the perimeter? Well, in each case, we're multiplying by 4, right? So our explicit formula would just be 4 times whatever the nth term is, okay? So if we have a side of 6, right, then the perimeter would be 24. If we had a side of 7, the perimeter would be 28. All right, now how about the area? Well, we already talked about this. We get the area by taking the length of the side, which is the same as n, and squaring it, right? Length times width is the same as squaring. So 1 squared is 1, right? 3 squared is 9. 5 squared is 25. Okay, so the explicit formula here would be take n and square it. So if we have the 6th term and a length of 6, that would give us an area of 36, right? 6 times 6. And then for 7, we would have 49. Okay, so this is an example of the explicit formula. These can be a little bit harder to recognize, but the key is to compare, right, the value of n. So whenever you're working on these problems, it's always good to just write the n value at the top and then say, how do I get from that n value down to the corresponding number in the sequence? Can we figure out what that formula or mathematical operation is? So notice that all of these formulas always had n as part of the variable, okay? That's the key way you can recognize an explicit formula. It's always going to have n in it, and it depends on what that value is, because that's the term that we're trying to find, right? Whether it's the 1st or the 5th or the 10th or whichever. All right, let's look at a couple more examples of each type of formula, 2 with recursive and 2 with explicit formulas. So here's our pattern, 2, 6, 18, 54, 1, 62. How do we get from one to the next? Well, hopefully this one's pretty obvious, right? We're going to just simply keep multiplying by 3 to get to the next term. So what would the recursive formula look like? Well, we always start with a sub n, and then on the other side, we're going to do something to the previous term. So in this case, we're taking the previous term, a n minus 1, and multiplying by 3. It's as simple as that, right? Take the previous term, multiply it by 3, and we get the next term. That's how we get from 2 to 6, from 6 to 18. Right, 2 to 6, 6 to 18, 18 to 54, multiplied by 3. The other thing we always want to include is our starting condition. So the first term is equal to 2. Now let's use this to find the next couple terms, right? So if we want to find the 6th term, we're going to take the 5th term and multiply it by 3. So that would be 162 times 3 gives us 486. To find the 7th term, we take the 6th term and multiply it by 3. So 486 times 3 gives us 1,458. You can see numbers are going to get very large very quickly when we're multiplying. All right, let's look at one more example of recursive. -2, -1, 0, 1, 2. So how are we getting from one to the next? Well, this one's fairly simple. Pause it and see if you can figure it out, and then write the recursive formula. Okay, so our pattern is simply add 1 to the previous term. So the recursive formula would be a sub n, always start with that, equals the previous term, and then add 1. And our starting condition is -2. Now let's use this to find the 6th term. So we take the 5th one and add 1. So 2 plus 1 gives us 3. To find the 7th term, we start with the 6th term and add 1. So 3 plus 1 gives us 4. Okay, simple example there. All right, let's look at a sequence that we want to write the explicit formula for. So we want to describe the pattern, figure out how do we get from one to the next, write the explicit formula, and then we're going to find the 12th term. Notice we're going to go jump ahead here, not just find the next one in the sequence. All right, so what's the pattern? Well, the pattern that we're looking for here is how do we get from the n value to the term value? So how do we get from 1 to 4, or 3 to 6, or 5 to 8? okay? So if you look at this for a minute, we can get from 1 to 4 by adding 3, 3 to 6 by adding 3, 5 to 8 by adding 3. So we're going to add 3 to whatever the term number is to give us the term value. So here's what the explicit formula would look like. A sub n is just going to be whatever our n value is, and then add 3. Okay. Notice our formula for explicit will always have n as our variable in it. Now, what's our starting condition? Well, it's not necessary that we list it, but it's good to go ahead and include that. Okay, because we could always find our starting condition. If we put 1 in for n, 1 plus 3 gives us 4. Now, let's find the 12th term. So to do this, we're going to put 12 in for n. So 12 plus 3 gives us 15. The 12th term would be 15. Now, if you need to prove that to yourself, right, you could go ahead and write out all the terms till you get to the 12th term, but you would then see that that value is 15. All right, one more. See if you can do this one. I'll pause it while you work on it. All right, 4, 7, 10, 13, 16. Okay, and again, we're adding 3 each time. But the key pattern we're looking for is how do we get from 1 to 4, 3 to 10, 5 to 16? Maybe not quite so obvious this time. And some of these that get a little trickier may be more than one operation. It may be more than just addition or multiplication or subtraction. So, anybody see this as the pattern? Take the n value, multiply by 3, and then add 1, right? 1 times 3 is 3 plus 1 gives us 4. 3 times 3 is 9 plus 1 gives us 10. 5 times 3 is 15 plus 1 gives us 16. Okay, so here's what the formula would look like. Take the n value, multiply by 3, and then add 1. Starting condition, again, don't have to, but it's always good to list it for even explicit formulas. Now, what would the 12th term be? What are we going to do with that value of 12? Where we're going to put it in for n for the 12th term. So 3 times 12 plus 1 would give us 37 for the 12th term. Okay? All right, so we've had some practice identifying mathematical patterns, and we now know how to write an explicit formula and a recursive formula for finding the next term or any term in a sequence. Okay? So there is an assignment in Google Classroom that goes along with this. Go ahead and take a look at it, and we'll review that at our next lesson.